Imagine that you're on a carousel. This is a bird's eye view, and it's not going to be very pretty drawing, so bear with me here. But say you're on a carousel, and here's the center where the calliope is, and I don't know, there's usually paintings and stuff that you can look at as you go around. And let's say that you're on a horse here. There are usually horses around kind of close to the center, and then there's some a little farther out. There's a reason I'm not an art teacher. And then there's some, even farther out, closer to the edge. And we're going to pick a horse for you near the center and a horse for a friend closer to the outside. And you're going around this carousel. Let's say it's going in this direction. And as you go, remember we've talked about the fact that angles are the same size regardless of whether they're close to the center or farther away. So if we do, for example, we do this, we can see the angle through which you go at you and your friend are traveling at any given time. So let's say it takes, I don't know, 10 seconds to get from here to here. It's also going to take seconds to get from here to here. Looks smaller, right? But in terms of the amount of rotation, it's the same. If you stand here and face out in this direction and then turn so that you're facing in this direction, right? You're going to turn the same amount whether you're looking at this person or looking at this person. You're going to turn your body if you're standing here facing in this direction and then you turn your body so you're facing in this direction, you're going to turn the same amount regardless of who you're looking at. So the angle doesn't change. So if it takes 10 seconds to get from here around to here for you, it's also going to take 10 seconds to get for your friend to get from here around to here, right? And so your angular speed is the same. On the other hand, as you travel through that distance, you are actually not going that far. If you were to walk from here to that, from the initial ray to the terminal ray at the angle, it wouldn't take you, you're not covering very much distance. But your friend, on the other hand, is going to have to cover a lot more distance to carve out the same angle. And that's because they are at a greater distance from the center of the circle. The radius of the circle they're going around is much bigger than the radius of the circle you are going around. So your linear distances are different. So your linear speeds will be different. Now the terminology is a little bit uh, confusing here because we're talking about linear speed, but what we're actually discussing is the speed around a curve. So this is not a line, it's a curve. But it is a linear speed in the sense that you are traveling along a distance measurement rather than through an angle. Okay, so we're talking about a linear speed. Your linear distance here for your friend is greater than it is for you, even though your angle that you're going through is the same. So if you go back to, again, very early algebra, hopefully you know the formula distance equals rate times time. Because we're getting more advanced in our mathematics, we're going to give some more precise terminology to these terms. That distance equals rate times time is a very general formula. It can be used for a lot of different circumstances. But distance in this particular case is the distance around the circle. So for you, it's going to be this short yellow line, and for your friend, it's going to be this longer yellow line. And that's what we're calling S. So I'm going to rename D to S. Now, rate is another thing. We need to be a little more specific here than we have been in the past. Rate is a very generic term. We need something a little more specific. We're going to use the word velocity, so we're going to use the letter V. Let me make a note of that here. Velocity is a kind of rate specific to the change of position, right? You can have a rate of 47 miles per hour. That's a That's a velocity because you're changing position at a particular speed, if you will. But you can also have a rate of 47 gallons per minute. Now that's a rate, but it doesn't relate to distance and time and all that kind of stuff. So we needed a word more specific to our distances, right? So we're going to use the word velocity. Velocity is a rate of change. It's still a rate, but it's specific to our purposes. And time is still time, so we're just going to leave that time. I should also put down here that S is equal to arc length, just as a reminder. And so we have now what feels like a new formula, but it's really just based on distance equals rate times time. Now, if I divide both sides of this by t, I get s over t equals v, or v equals s over t. And that's just a little bit of algebra, but that's the form it's in your textbook. You can actually use it in either form, but what we're looking for here is linear speed. This is a formula for linear speed. And what it says is your linear speed, or your velocity, is going to be equal to the arc length, the yellow line, divided by time. And that's it. Once you know what the arc length is and the time is, you just plug them in and do the arithmetic. Sometimes you might know the time and the velocity, and you're looking for arc length. Well, in that case, you would use this version of the formula. Sometimes you know velocity and arc length and you're looking for time. So it doesn't matter what form the formula is in. What matters is that you understand what the parts are and what to plug in for each of those parts. All right, I'm going to put a little cloud around this work, and I'm going to write a new version of distance equals rate times time over here. And this time we're going to talk about different rates and different distances, right? The distance I want to talk about this time is the distance you travel in this rotation, right? The rotational distance. And as we talked about earlier, the rotational distance is the same for you and for your friend, even though the linear distance is less for you than it is for your friend. All right, so the rotational distance here is theta. Right? How many radians did you sweep through? How far did you rotate? How many degrees did you spin? Right? That's what they mean by distance in this particular case. Now, as with our previous example, time is going to be the same as time in both versions of our formula, and rate is something we're going to call angular, I should call this linear velocity. This is going to be called angular velocity. Angular. Now, even if I say it right, I can't spell angular velocity. It's actually really hard to talk and write at the same time. We're going to use a Greek letter. This is our first use of a Greek letter in this case. We're going to use the Greek letter omega, little lowercase omega, and it looks like a little bit kind of a curly Q, little W. Okay, that's the Greek letter omega. The capital letter omega looks like this. That's the last letter in the Greek alphabet. That's the lowercase one, right? Omega. So here we have another new formula, except it's really not. It's just distance equals rate times time again. We've just relabeled what our distance and our rate are. Once again, if I divide both sides by time, I get theta over t equals omega, or omega equals theta over t. And this is another formula for speed or velocity, but in this case, it's for angular velocity, right? How fast you are turning through how fast you're rotating around the carousel is determined by the angle you have rotated through in this amount of time, right? So this is the formula for angular speed. Now, I'm not crazy about the last formula in this subsection, but it's in your textbook, so I'm going to walk through it. If you take the formula S equals R theta, that's the one that lets you find the arc length of a circle, how far around the circle you've gone. If you multiply the radius of the circle times the angle you've gone through, right? S equals R theta. Remember, this is the one where theta has to be in radians. And then if we look back at this formula, and we notice that theta can be written as omega t, so that means we can rewrite this formula as S equals R instead of theta, we're going to write omega t. So I've written S equals R theta as S equals R omega t using a different version of this formula, right? I've used this version of that formula to sort of substitute in for theta. What I'm now going to do is take this version of S and replace this S with it. So my new formula here is velocity, linear velocity equals S over t, but S can be written as R omega t, and then of course t cancels. So this implies that velocity, it can be written as R times omega. What this gives us is a way to find the linear velocity if we know the angular velocity. Equally, if we divide both sides by R, I don't think this is in your textbook, but it's pretty easy to extend. So if I start with V equals R times omega, and I divide both sides by R, I get omega equals V over R. So here, if I know the angular velocity and the radius, I can find the linear velocity. Here, if I know the linear velocity and the radius, I can find the angular velocity. So it's kind of a direct line between the angular and linear velocities, which is perhaps handy. I don't recall ever having used it, but there it is. So we'll see if that comes up again. But in the meantime, that is the last video I want to do for this section, 5.1. I've not done any examples in this subsection in this topic, and that's primarily because I've really wanted to keep the videos as short as possible. This one's still a little over 10 minutes. I'm getting better. I'll keep working on it. There are also a lot of subsections in section 5.1, so there are a lot of videos, and I apologize for that. That's just the way that the textbook has sort of been arranged. So hopefully as we go forward, there won't be quite as many subsections in a section, so there won't be as many videos for you to watch. At any rate, I will see you in class, and we will talk about all of these things. And the next time you're watching videos, hopefully before I see you, depending on whether this is a 2-day-a-week class or a 5-day-a-week class, you may have to watch another section's worth of videos before you come to class at our next session. So at any rate, I wish you all the best, and I'll see you in class.